Welcome, curious minds, to another deep dive.
Hello, everyone.
Today, we're plunging into the invisible world of wireless signals. It's this place we all rely on constantly, right? But we rarely give it a second thought.
Absolutely. It just works until it doesn't.
Exactly. And specifically, we're tackling one of the biggest, most pressing challenges facing our increasingly connected planet.
Yes.
How do we enable more and more devices, billions of them, to communicate seamlessly, efficiently,
And, without everything just jamming up.
Especially when the airwaves, the spectrum, are already so crowded.
Precisely. So we're diving into some really fascinating research today. It's about
We're going to show you how a clever combination of, teamwork among devices
teamwork. Okay.
and a touch of redundancy, sending things more than once, is proving to be a bit of a game changer.
Making things more robust, I guess.
Exactly. Making next-generation technologies surprisingly robust and reliable, even in, the most challenging wireless environments.
And we're grounding this in some solid research.
We are. We'll be pulling insights from a really pivotal paper. It's titled On the Performance of Cooperative Spectrum Sensing Under Binary Erasure Reporting Channels.
Okay, that's a mouthful. Who are the authors?
It's by Parmar.
Captain, Kumar, and Chauhan. And what's great is that this research offers some incredibly practical solutions to these fundamental wireless problems.
problem.
About it. Everything seems to be wireless now.
It does. From the smallest smart home devices, your thermostat, your lights, wearables, the phones in our pockets,
To the huge stuff too, right? Industrial sensors, connected vehicles.
massive industrial sensors, seamlessly connected vehicles, the intricate backbone of data centers, the Internet of Things, or IoT, is demanding an absolutely monumental number of devices to communicate wirelessly.
And it's not slowing down.
Not at all. Every single year, literally billions more things are coming online.
All needing a piece of that invisible pie we call the radio spectrum.
It's like an insatiable appetite for connectivity.
It really is. And this leads us directly, inevitably, to the core.
Exactly. And there's only so much of it available. For decades, the main strategy, the predominant one, has been to rigidly allocate fixed portions of the spectrum to specific users or services.
Like this slice is for TV, this one's for mobile phones.
Yeah, imagine assigning certain frequency bands exclusively to TV broadcasters, while others are locked down for cellular carriers. And this is regardless of whether they're actually using them, actively transmitting at any given moment.
And that just seems inefficient if they're not using it.
It is. This outdated fixed allocation strategy has led to some serious, almost baffling inefficiency. Picture this. Way back in 2002, the Federal
To the cars in certain lanes, even when those lanes are completely empty for long stretches of time.
Which means
It's a traffic jam and waiting, even with open road. A recipe for congestion down the line.
okay. And why should you, our listener, care about this sort of regulatory and technical stuff? How does it affect us?
Well, it affects you directly. If we don't address this fundamental inefficiency, we're looking at inevitable bottlenecks. And those will directly impact your daily digital life.
Like my Wi-Fi slowing down.
Imagine slower Wi-Fi speeds. Yeah.
frustrating online calls or streaming that keeps buffering, drop cellular calls right in the middle of something important.
Or my smart speaker not responding.
Or your smart home device.
coming up. And this is where something really transformative called cognitive radio, or CR, steps in. It's designed as an intelligent, dynamic solution.
Cognitive, like thinking radio.
Sort of. Think of CR as a highly intelligent, self-aware system designed for dynamic smart sharing. It allows what are called secondary users, or SUs.
That's us, our devices.
That's essentially your device, yes.
Yeah.
Your smart sensor, your connected car. It allows these SUs to opportunistically access spectrum bands that are licensed.
Interfere with the primary user.
That's the absolute key. The critical mechanism for these secondary users to gain this opportunistic access is called spectrum sensing, or SS.
Sensing the spectrum. Makes sense.
Before any secondary user can even think about transmitting, it must first sense if the channel is truly empty.
It's not just optional then.
No, it's fundamental, a requirement, to ensure that it doesn't cause any harmful interference to the primary user who actually holds the license for that spectrum band.
So it's about being a good neighbor in this invisible wireless neighborhood.
A very good analogy. You have to listen carefully before you speak.
Okay, so how do they do this sensing? Are there different ways?
There are
because it doesn't require any prior knowledge about the primary user's specific signal characteristics. You don't need to know exactly what they sound like.
So it's more adaptable.
Highly adaptable in diverse scenarios, yes. You're basically just listening for any energy, any whisper of activity in the band to determine if it's occupied or free.
Like putting your ear to a door to hear if anyone's inside without knowing who it might be.
Exactly like that. A very basic but effective check.
Okay, simple enough. But is it foolproof? Are there challenges?
now here's the initial significant hurdle. A single cognitive radio user, just one device trying to perform spectrum sensing, faces substantial challenges.
Then there's shadowing, where physical obstacles, think large buildings, hills, dense foliage, directly block signals. They create dead zones where the signal just can't reach.
Like being behind a big pillar and losing phone signal.
Exactly. And of course, there's always path loss. Signals naturally weaken over distance regardless of obstacles just because their energy spreads out. Like shouting across a field, the further away, the fainter it gets.
Fading, shadowing, path loss. Makes sense. Anything else?
Yes, and this one is particularly tricky, almost insidious in practice. It's called a hidden node problem.
Hidden node, what does that mean?
Imagine your single secondary user, your device, is
transmitting, but you just can't hear them directly from where you are.
That sounds like a recipe for disaster. A critical blind spot.
It is. These pervasive impairments, the fading, shadowing, path loss, and especially this hidden node problem, they severely degrade the accuracy of a single user's sensing capabilities.
And that leads to bad outcomes, I imagine.
Two major, equally problematic outcomes. Either the secondary user wrongly assumes the channel is free, starts transmitting, and causes harmful interference to the primary user.
That's a huge no-no. Regulators hate that.
Right. Don't bother the license holder.
Or the device errs on the side of caution, maybe because the signal is weak and confusing, and it misses out.
sense.
This approach is specifically designed to overcome the inherent limitations of single detectors by intelligently utilizing something called spatial diversity.
Spatial diversity, meaning devices in different places.
Precisely. Instead of just one device listening, you have multiple cooperating secondary users, or CSUs,
working together. Each one senses the environment from its own unique vantage point.
So one might be blocked by a building, but another one might have a clear view.
That's the idea.
The process is pretty well defined. Here's how it generally works.
Lay it out for us.
Okay. First, each CSU individually performs its sensing that energy detection we talked about and makes its own initial decision, a simple binary thing. 0 if they think the channel is idle, 1 if they think it's occupied by a primary user.
Okay, step 1, individual decisions.
Step 2, they don't act alone. They share these individual detection results, either 0 or 1, with a central aggregation point.
The central hub.
Exactly. It's called the Fusion Center, or FC. You can also think of it as the Cognitive Base Station, or CBS.
It acts as the brain of this cooperative network.
Got it. So all the little sensors report back to the main brain.
Then step 3, the Fusion Center diligently collects all this individual decision.
Yes. If, say, a significant majority of the CSUs report 1, meaning they collectively think the channel is occupied, then the Fusion Center declares the channel occupied.
And if most say 0,
then it decides the channel is idle. It's basically a democratic vote on the state of the airwaves based on the collective wisdom of the crowd, or the sensors in this case.
That sounds pretty robust. Does it work well?
Yes. DSS has indeed been proven to be very effective. It strikes a crucial
balance between getting high-spectrum sensing accuracy and keeping the complexity of the individual sensing devices reasonably low.
So you don't need super fancy individual sensors if you have enough of them.
access overall. It's a solid approach.
Okay, cooperative spectrum sensing sounds like the ultimate team effort then. A real silver bullet for this spectrum sharing problem. Teamwork, better accuracy, more efficiency, seems perfect.
It does sound great, doesn't it?
I sense a but coming. As often happens in these complex systems, there's usually a hidden snag, right? A crucial assumption that if we overlook it, could undermine the whole thing.
It's a very astute observation, and it highlights precisely what we might call the dirty little secret
of traditional cooperative spectrum sensing, or at least how it's often modeled.
Okay, what's the secret?
In much of the existing literature, a critical, often unstated assumption has been made.
Well, think about it. It's almost an ironic flaw. These reporting channels are themselves wireless.
Of course, they're not physical wires.
No, they are inherently susceptible to the very same issues that plague the initial individual single detector sensing. We're talking about the same fading, the same shadowing, the same path loss.
Even the hidden node problem could affect the reporting link.
Potentially, yes. So, if the reports from the CSUs are corrupted, garbled, or even
completely lost on their way to the Fusion Center,
then the Fusion Center's decision is based on bad data.
Exactly. The FC's final decision can be fundamentally flawed, even if the individual
closed loop of imperfection.
Which is precisely why accurately modeling that imperfection and then devising a robust solution to overcome it becomes paramount.
It makes sense, like your detective analogy earlier with great detectives, but if their walkie-talkies are unreliable,
The whole investigation falls apart.
Imagine trying to make a critical, time-sensitive decision based on faulty or garbled information from your team. The outcome could be disastrous.
And in the wireless world,
That could translate to
In the paper, did attempt to model these imperfect channels. They moved beyond that perfect channel fantasy.
and how do they model it?
They often used a model called the binary symmetric channel, or BSC.
Binary symmetric channel. What does that mean?
In a BSC model, a transmitted bit, say a 0 representing idle, could flip to a 1 representing occupied, or vice versa, with a certain probability.
So errors meant the data was corrupted, changed from 0 to 1 or 1 to 0.
Yes. It essentially assumed a single isolated bit of the decision was transmitted.
and it might get flipped along the way. You receive something, but it might be the wrong something.
okay, that accounts for errors, but is it realistic for modern systems?
Well, this is where the paper we're focusing on introduces a really
reflects how modern real-world wireless communication truly works far beyond just theoretical single-bit flipping.
So the distinction is between getting the wrong answer, BSC flip, and getting no answer, BC erasure.
Exactly. BSC is like getting a typo you read HTT instead of you got something but it's wrong. BSC is more like an email that just fails to load entirely or gets flagged as corrupted and unreadable. You know something was sent, but you can't decipher it. It's lost, erased.
Why is erasure behavior more common now? What changed in communication systems?
It comes down to how data is packaged and checked for
errors. Crucially, in real scenarios, a single raw bit representing a decision that 0 or 1 is not transmitted in isolation is way too fragile.
Right.
resides.
Okay, header payload.
Yeah.
What else?
And finally, critically, there's a trailer. And the trailer usually contains something incredibly vital for data integrity. The frame check sequence, or FCS.
FCS frame check sequence, what does that do?
Think of it as a built-in, highly sophisticated error checker for the entire frame. It's designed specifically for error detection and correction. It's like a digital fingerprint of the data.
Okay, so how does this FCS lead to erasures in the BEC model?
Here's how the BEC logic works.
With this frame structure and why it's a much better fit for today's networks. When a frame travels wirelessly, errors can creep in, right? Fading, noise. Now, if the errors that occur
An erasure event.
Okay, so minor errors get fixed, but what if the errors are worse?
Right. If the errors in the frame are more than that correctable limit, if the corruption is too widespread for the FCS to fix,
Then what? Does it try to guess?
no. And this is the critical point. The FCS can still reliably detect that there are too many errors, but it simply cannot correct them. In this scenario, the frame is not passed along with potentially flipped bits, like in BSC. Instead, it is deliberately and completely discarded by the receiver.
Discarded, erased.
Exactly. This happens with probability P.
modern digital communication protocols, think Wi-Fi, 4G, 5G, they prioritize data integrity above almost everything else.
Better no data than wrong data.
Absolutely.
discards the corrupted data. It's universally considered safer to have no data than to act upon incorrect or misleading data. This erasure then might trigger a retransmission request in some systems, or in our CSS case, it simply means the Fusion Center doesn't receive a usable report from that particular CSU for that attempt.
So the FCS is like a very strict quality control check, pass-fail. And fail means erasure.
That's the perfect way to put it. Pass-fail. Minor issues get fixed. Pass.
Major issues lead to discard, fail, erasure. That's why BEC, modeling loss or erasure, is far more representative of how modern wireless data is handled.
Okay, that makes a lot of sense.
Findings, shown clearly in figures like Figure 5 and detailed in Table I, painted a really clear picture of degradation. They looked at performance under different error rates.
Okay.
They fixed the probability of false alarm, QF, at a typical value, say 0.1. Then they looked at the probability of detection, Q how well you detect the primary user.
Right, QA needs to be high.
Exactly. They found that QA takes a serious hit as the reporting channel gets worse. For instance, when P, the probability of erasure was just 0.1, meaning 10%
of reports get lost.
Yeah.
The QI was 0.6124. Okay, not perfect, but decent.
But what if the channel is worse?
When P increased to 0.3, meaning a full...
channel imperfections or modeling them incorrectly is such a critical oversight.
Absolutely. I mean, the very accuracy that cooperative spectrum sensing was designed to provide its whole reason for being is severely compromised if those reporting channels aren't reliable.
That's genuinely alarming. Our smart system for sharing spectrum, relying on teamwork, gets kneecapped by the very same wireless issues it's trying to solve. It's a major vulnerability.
It is.
So, okay. We have a clear problem. Imperfect wireless channels mess up our smart spectrum sharing, even with cooperation.
What's the clever fix? What did Parmar and the team propose to get around this?
Okay, so we've pinpointed the Achilles heel. Those imperfect reporting channels modeled by BEC erasing crucial information.
Proposes a clever repetition code-based algorithm.
Okay, tell me more. How does repeating things help?
Think of it like this. You have a really important message to send over a crackly phone line, right? Maybe coordinating something critical. Instead of just saying it once and hoping for the best.
You say it again, maybe even a third time.
You repeat it a few times, exactly. Even if some parts get lost in static or garbled, the chances of at least one clear transmission getting through become significantly higher.
I see. Increasing the odds of
success.
That's the core intuition behind this repetition-based algorithm, sending just enough extra information, or rather the same information multiple times to help guarantee success.
Before, each cooperating secondary user, each CSU, performs its energy detection independently, makes its initial binary decision. 0 for idle, 1 for occupy. Nothing new here, that's the foundation.
Individual sensing done. Now what?
Step 2, multiple copies. This is where the crucial innovations of repetition begins. Instead of preparing and sending just one frame containing its decision, each CSU now creates R, where R stands for repetition length
copies of its decision frame. So if R is 2, it makes 2 identical copies. If R is 3, 3 identical copies, and so on.
And it sends all of them.
It reports all R copies to the Fusion Center.
It immediately applies its robust error detection and correction mechanisms, thanks to that frame check sequence we discussed. It's vetting every single incoming report, every postcard.
What happens if a frame is okay?
If a frame is received correctly, meaning no errors, or only correctable errors are detected by the FCS, then the Fusion Center successfully retrieves the decision, the 0 or 1, from that frame. It marks that copy down as good.
And if the frame is too corrupted, like our BEC model
Predicts.
If a frame has too many errors more than the C bits the FCS can reliably fix, then, true to the binary erasure channel model, that frame is simply discarded.
Erased.
Result from the first frame received from any CSU, the other frames received from that CSUs are not processed.
Oh, that's clever. So if the first copy gets through clean, it doesn't even bother looking at the others from that same sensor.
Exactly. It's a key optimization. Why waste precious processing power, energy, or time decoding subsequent identical copies if you already have the control message?
That saves resources. It's especially important in a busy wireless system with potentially many sensors reporting.
Hugely important. It reduces computational load, saves battery life on the FTC side. It's about being effective, not just wastefully repetitive.
Get the message once reliably, then move out.
Okay, smart reception. What's the final step?
Step 4, final decision. Once the Fusion Center has meticulously tried to retrieve decision,
Can transmit.
Precisely. That final decision guides whether secondary users can transmit or must wait.
Okay, let's make this concrete. Can we use that example from figure 3 in the paper with K5 CSUs and R2 repetitions?
Absolutely. It illustrates the process perfectly. So K5 sensors, each sending R2 copies of their decision. CSU1 sends 1, occupied, sends 1, 1. Let's say the first frame gets erased, too many errors. If the second frame comes through correctly, FC checks it, it's good. FC records 1 from CSU1.
Okay, 1 more.
CSU2 sends 0, idle.
sends 0 hodoto. The first frame arrives perfectly, FC checks it, it's good. FC records 0 from CSU2, and because it's smart.
It ignores the second 0 from CSU2.
CSU5 sends 1, sends 1, 1. First frame arrives correctly. FC checks it, good. FC records 1. Ignores the second frame.
Okay, so the final tally at the Fusion Center is 3 ones and 2 outs.
Correct. So at the very end of this collection phase, the Fusion Center applies the majority rule. 3 ones versus 2 outs.
Majority is 1, so the final decision is occupied.
The Fusion Center declares the channel occupied. And this example beautifully demonstrates how even with some reports being
Erased from CSU1 and CSU4, the system, thanks to repetition, still manages to derive an accurate overall picture based on the reports that did get through.
That's
into a resilient one.
That's a great way to summarize it.
Okay, the theory sounds solid, the example makes sense. But now for the big question. What do the actual performance numbers say? Does this repetition really work as well in analysis as it seems to in theory? Is it worth the overhead of sending extra copies?
Right, the moment of truth. Does the data back up the intuition? This is where the paper gets really compelling, providing that proof through detailed analysis and some quite remarkable results.
So how did they structure the analysis? What were they comparing?
To set the stage for a rigorous comparison,
The researchers meticulously examined the CSS performance across 3 key distinct scenarios. This allows for a really clear understanding of the benefits.
what were the 3 scenarios?
bad things get without a fix.
Okay, the problem scenario.
And third, the proposed solution. The repetition-based algorithm deployed under those very same imperfect BEC reporting channels. This shows if the fix actually works.
Perfect versus problem versus solution. A very clear comparison structure.
Exactly. And for consistency, to make sure they were comparing apples to apples in their theoretical analysis, they made some standard simplifying assumptions.
Like what?
They assumed that all the cooperating secondary users, the CSUs,
Experienced the same signal-to-noise ratio, SNR, and had the same noise variance. This just helps isolate the impact of the reporting channel errors and the repetition itself without
You want Q to be low, right? To avoid wasting opportunities.
exactly. A high Q means you're blocking access to available spectrum unnecessarily, reducing efficiency.
And the second metric.
The probability of detection, or Q, this is the chance the system correctly decides its channel is busy when it actually is busy.
And you want Q to be high to protect the primary user.
Absolutely critical. A high Q is paramount because it directly prevents harmful interference to the primary user, which is the cardinal sin in spectrum sharing. So the goal is always this balancing act. Maximize Q,
protect the PU while minimizing Q, use spectrum efficiently.
Max Q, min Q. Got it. Did they validate their models first?
Yes, and this is crucial.
perfectly. As illustrated brilliantly in Figure 4 of the paper, the plot from the theoretical equations and the plot from the simulation results exactly overlap. Not just close, but identical.
That's fantastic. It means their math accurately reflects reality, giving huge confidence in their findings.
Huge confidence. It confirms their model is sound before they use it to draw conclusions.
Okay, model validated. So first, did they confirm how bad the problem really was with traditional CSS under
Imperfect channels.
They did. With the validated model, they could confidently revisit that core problem. Figure 5 in the paper clearly and dramatically demonstrates the performance of
probability when the erasure probability p was 0.110% loss was 0.6124. But when pan increased 0.3, 30% loss, QD plummeted to just 0.4416.
That's that huge 38.68% degradation again.
Precisely. It underscores just how critical this issue is. The more errors in reporting, the less reliable the fusion center's input, leading directly to poor system performance and a much higher risk of interfering with primary users. It confirms the problem is real and significant.
Okay, problem confirmed and quantified. Now for the solution. The repetition
Algorithm. Did it help?
This is where we see the triumph of repetition, beautifully illustrated in Figure 6 and quantified in Table 2. The results are clear. As the repetition length R increases, the
focusing on IQ echo point 1 point again for consistency. When R1, that's no repetition, just traditional CSS under the imperfect channel with P0.1, the QD is 0.6124. That's our flawed baseline. But then when they increased R to just 2, only one single extra copy sent per sensor, QD jumps significantly to 0.6809.
That's an 11.19% improvement we talked about, just from one extra copy.
And 11.19% higher QD, yes. From an engineering standpoint,
that's a massive gain in detection probability for such a minimal increase in redundancy. It could absolutely be the difference between a system working reliably or not.
Okay, R2 gives a big boost. What about...
Setting more than 2 copies for this P0.1 scenario simply doesn't yield any further performance gains. And this is incredibly important for efficiency. It tells system designers, you don't need to overdo it. There's an optimal point of redundancy, or 2 in this case, that delivers the maximum benefit without introducing unnecessary overhead.
Overhead like using more bandwidth, more battery power, more processing time.
All of that. It avoids wasting resources. It's an engineer's dream
Finding that sweet spot that maximizes performance while minimizing resource expenditure. This translates directly to better real-world systems supporting more devices, maybe faster speeds.
It compares the performance of the repetition-based algorithm with RT2, known as the imperfect channel, directly against the performance of traditional CSS under a perfect error-free reporting channel, our gold standard baseline.
And the result?
The finding is truly profound and game-changing. The repetition-based CSS algorithm with just 2 repetitions, R22, performs similar to traditional CSS under a perfect reporting channel. The performance curves basically lie on top of each other.
Wait, let me process that. With just
2 copies, sending messages over a faulty erasing channel, they achieved the same performance as if the channel was perfect.
Think about that. It's transformative.
It's as if they took a noisy, unpredictable, error-prone wireless reporting channel and, through this simple, intelligent repetition strategy, made it behave like a perfectly clean, error-free one, at least in terms of the final outcome for the CSS decision.
That is quite a testament to intelligent system design. Adding just a little bit of structured redundancy overcomes the inherent chaos.
Precisely. By acknowledging the imperfection using BEC and tackling it smartly with repetition, they achieved near-ideal performance.
This truly feels like the breakthrough moment. It makes reliable, accurate communication in these challenging wireless environments seem much more achievable, much more practical.
This research offers a concrete, elegant way to essentially sidestep that unreliability at the crucial reporting stage.
Allowing us to build predictable, high-performance systems even when the airwaves are messy.
It dramatically simplifies some of the most daunting design challenges for next-generation wireless networks. A huge aha moment.
Okay, so RE2 worked wonders for P0.1, but does the amount of repetition needed change if the channel is worse? Like, really bad?
Excellent question. And yes, the paper diligently studied this too. They looked at how the required value of repetition length R changes depending on the severity of reporting channel errors,
The value of P.
Where do they show that?
This crucial practical guidance is shown clearly in Figure 8. It confirms it's not a one-size-fits-all solution. The optimal R needs to adapt to
Almost half the reports are getting lost.
a truly tough environment. And logically, you'd expect to need more repetition to compensate.
And did they?
Yes. The paper shows that for P0.4, it requires RE5 repetitions to match the performance of CSS without reporting channel errors.
R5. So you need to send 5 copies in that really bad channel scenario to get back to that perfect channel level of performance.
Exactly. It's like a sliding scale.
Yeah.
The worse the static on the line, the more times you have to repeat yourself to be sure the message gets through clearly.
But the key is, even for a very bad channel, there is a value of R that can recover that ideal performance.
That's the crucial takeaway. This analysis provides incredibly valuable, practical
accordingly.
That's certainly a potential next step in system design that this research enables. You can build systems that dynamically adapt R based on current channel conditions, ensuring critical data gets through reliably while also being efficient when the channel is good.
This research feels like it fits perfectly into that bigger picture of making wireless communications smarter and more efficient, especially for things like 5G, 6G, and massive IoT.
Absolutely. It directly informs the design of future networks, particularly where you have
Billions of devices needing reliable, often low-power communication in potentially contested spectrum.
So pulling it all together, what does this deep
It's fundamentally about enabling the robust, highly efficient wireless communication that's demanded by the next generation of technologies. Things we're already starting to rely on, or will very soon.
Like the Internet of Things.
The massive growth of IoT, yes. The widespread deployment of 5G networks, and looking further ahead, 6G, and those future-critical, sometimes life-dependent applications.
Autonomous vehicles, smart cities, remote healthcare.
Fully autonomous vehicles needing constant, reliable
Updates. Deeply integrated smart cities managing traffic, energy, safety, precision remote surgery. All of these rely fundamentally on accurate, timely
It also really highlights how crucial it is to get the models right, doesn't it? Understanding the real-world behavior of these wireless channels.
absolutely critical. By moving from those overly simplified models, like the binary symmetry channel perhaps used in the past, to a much more realistic one, like the binary erasure channel.
Would reflect how modern protocols actually work, prioritizing integrity by discarding corrupted data.
By doing that, researchers can design far more effective and practical engineering solutions. It's about building solutions that genuinely work in the messy, unpredictable reality of our wireless world, not just in idealized mathematical simulations.
ensuring data fidelity where it truly matters most.
This whole deep dive really underscores how intelligent system design can triumph over apparent limitations. By acknowledging
It truly allows us to unlock vast amounts of underutilized wireless spectrum, potentially transforming a scarce resource into something more like a shared abundance, managed intelligently. This isn't just an academic exercise, it's laying the groundwork for making our connected future possible, reliable, and efficient for everyone.
A fantastic summary. So, for you, our curious listener, reflecting on everything we've unpacked today, here's a final provocative thought to chew on.
Let's hear it.
Consider how this
core principle, we've explored the principle of intelligent redundancy, of sending just enough extra information, just the right amount of repetition to guarantee success without